Okay. So just give a quick example, right? If your stress A and stress B are at this point, means your stress A is 50, your stress B is minus 50, right? So if we were to draw Mohr circle now, so this is 50, 100, normal stress, shearing stress clockwise, anti-clockwise, minus 50, minus 100, 50, 100, minus 50, minus 100, right? So our operating bracket is over here. Okay. So if your stress A and stress B, one is 50, the other one is minus 50. So this is your stress A, and over here, this is your stress B, right? So when we draw the circle, right, it is within the box. Right? It's within the box, as you can see, right? So if we were to have another, we have another one. So let's say over here we pick another point. Now this is outside already, right? You can see that. So this is equal to 50, and then one minus 75, right? So if we were to draw the same, so before we go on, so this at this point I call this condition number 1. So this is condition number 1, all right? Material will not yield, right? And then the next point over here, this is condition number 2, which is outside the boundary, right? When I say the boundary, I refer to this box over here. Okay, so this shape over here, right? Outside the boundary now, right? So what you see now, right? We have drawn this earlier. Okay, so this is our right, and then we have our vertical, right? So this is 50, 100 normal stress, shearing stress clockwise, anti-clockwise, minus 50, minus 100, 50, 100, minus 50, minus 100. Okay, and then the green box, our boundary bounded by the material properties, right? So now we have one point at 50, positive 50. Okay, let me, so this is your stress A, and then this is your stress B. So what we realize that when it's outside the boundary, right, like for this case, it just gone outside already. Okay, so condition number 2, material will yield. Okay, so basically anything that is inside here, inside the box or inside the yellow boundary, Okay. No yielding. Okay, material will not yield. When anywhere that's outside, okay, yielding will occur. Okay, like the two condition I show you. Okay, so this is Tresca criteria. Okay, so you hear me close to like 15 minutes talk about Tresca criteria. Let's do one difficult example, okay, on Tresca criteria. Okay, so you guys have the question. Let's look at this question. Again, this is not an easy problem. This is a difficult problem. Right. So this is another example. Okay. So what is given down here is the internal loading at a critical section along the steel shaft of a ship are calculated to be a torque of 23,000 pound-feet, a bending moment of 1,500 pound-feet, and an axial thrust of 2,500 pounds. Okay. If the yield stress for tension and shear, so stress yield is 100 kilopascal, and the shear in yield is 50, determine the required diameter of the shaft using the maximum shear stress criteria. Okay, so given that we have to use the maximum shear stress theory. Okay. So let's look at the structure first. Okay, so this is our structure. So this problem is very unique. Okay, there's no transformation. You have to start drawing your transformation. So over here, this will be our x, right? This will be your y, and over here, this is your z. Okay. So over here, we know that the 2,500 pounds is your P in X. Okay, so and then you write the PX is equal to minus 2,500 pounds, and it will induce compression. Okay, we know that it induces compression. And then you have torque. Okay, so this is torque along the x-axis, right? Because why is it a torque? Because it's rotating about the green or about the centroid. So again, like what I've taught you, this is the direction of the centroid of interest. Why that's the case? Why there's a centroid? Because we are going to place 4 elements. Okay, and we are going to place 4 elements. Okay, and later on I'll explain to you why 4. So you have element over here, you have another element over here, you have another element over here, you have another. So since I start putting the elements, let's give them a a name. Okay, so this is my element A, element B, element C, and element D. Okay, so you realize that in this question they did not give you any elements, but we're going to put those elements over there. Okay, exactly on those axes, and later on I can explain to you why. So now we know that there is a torque in the x along the x-axis, and it's rotating at 2,300 pound-feet, or you have to do 2300 multiplied by 12, which is equal to 27600 pound inch. Why we have to change to pound inch and not work in feet is because our stresses are what? In square inch, not square feet. Okay. And then we have a moment in Z, right? As you can see how the moment rotate. Over here with compression. On top it'll be tensile. So you know that mz is equal to what? 1500 pound feet, or 1500 multiplied by 12. So 1500 is 1500 is 18,000. Okay. Right. So we have to determine, okay, what else are we given? So we know that our stress U is equal to plus 100 times 10 to the power 3 psi, right? And then we also are given our shear stress U, which is equal to 50 times 10 to the power 3 psi, right? So based on Tresca, criteria, right? Stress U in compression is also equal to minus 100 times 10 to the power 3 psi. Okay. Right. So we also are given that our U stress is 50. Okay. So that's good thing. If we're not given, just take the 100 divided by 2. We also will get what? 50. Okay. So these are the information that we know now. Okay. So then the next thing that we're going to do, so the formula that we are going to apply, okay, so we know that stress X is equal to minus Px over A, right? And then plus minus, depending on the location, you have mz over izz multiplied by C. Okay, so C is the radius of the shaft, right? And then A is a cross sectional area of the shaft. And then the other equation that we need to use in terms of shear, right, is equal to Px over J multiplied by C. And again, C is the radius of the shaft. So J is equal to 2Izz. Okay. So in case I mean, if you don't know this, I will provide the formula and you can see. Okay. Now we know the formulas that we're going to use. The thing is, which element, okay, will observe the highest stress? Element A, element B, element C, or element D. And this is where we go to do failure analysis now. Okay, now we are going to do failure analysis. A very innocent question like this, but there are a lot of what? Steps that you